Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you out with number 56 in chapter 9. All right, it says something about a pair of asteroids. So what I've done here is I've drawn a pair of asteroids. This is my before impact. I wrote some data over here. I'm going to go ahead and call like maybe this one mass A, this one mass B. Now, the velocity of mass A, 770 meter per second, that's going to give it a momentum equal to MAVA1. Doesn't really matter the direction I put this in the picture. I'm going to go ahead and put this to the right here. So there's my MAVA1. And then it says that the velocity vectors make an angle of 20 degrees with respect to one another. So here's what I believe that means. Like, let's imagine for a moment, here's the momentum of mass B, MBVB1. And it says that the momentum or the velocity vectors make a 20-degree angle. So this is, I'd say, what they mean by that this guy is moving like this in this direction in such a way that these guys make a 20-degree angle, like I've got it now. So here's my picture one before impact. They hit and become stuck together. Now, if you kind of look at this system here, their momentum after the impact definitely is right and up. So they're going to have a single momentum vector maybe in this direction equal to MV. I'm going to put capital M V2 here. My capital M is going to be the sum of these two. Because they say stick together, we can treat it like one mass. This is going to have some sort of unknown angle, which you're going to have to calculate. So here's my picture one. Here's picture two. The 1 to 2 part, that's the impulse part of the picture. The impulse between these, so this is the time frame where these guys' momentums are changing. The force that this guy applies onto this guy is a normal force that'd be applied here at this surface in this direction, and delta t. And then the force that this guy applies this way, and delta t, that's Newton's third law, remember, that forces and hence impulses always appear in pairs. Now, problems like this, when you look at your physics text, they usually ignore the impulse diagram. But again, the impulse diagrams can be very important, especially in situations that are a bit more complex. So I think it's a good habit to get into drawing these momentum impulse pictures. So now, here's an angle, 20 degrees. You can write two momentum equations for this. Again, because the net impulse on the system is zero, momentum is conserved in any direction you want. So I would write an equation in this direction. That equation is going to involve the x component of this momentum vector, and it will involve this momentum vector as well. Over on the right, then you're going to need the x component of this vector. If I draw in the picture, it would be here, adjacent to the angle theta. So that should allow you to write out an equation for that. Then write yourself a momentum conservation in this direction. So when we look at this picture, that's going to be this momentum component. Now again, remember the hypotenuse is MV here, and this is opposite the 20 degrees. This guy does not have a momentum component in the y direction. Right, the 1 to 2 picture, net impulse is zero still, any direction you want to choose. And then the y component of this guy's momentum is here. Again, the hypotenuse here is capital MV. This guy is opposite theta. So you should be able to write yourself out two equations. And the two unknowns will be the V2 and the theta. The quickest way to solve it will be to take like one of these equations. Like let me call this equation 1 and this one equation 2. I would take equation 2, the entire equation, divide it by equation 1. If you do that correctly, you should end up with something like a number equals tan theta, and you're going to be able to find the theta. And then once you have the theta, go back to either of these two equations to get the velocity V2. So that should be enough to get you through it. I hope that helps. Have a great day.